Hey guys. Give it a few more minutes. How you guys doing this morning? I don't know if you noticed it, but our Zoom meetings are a little bit weird. I had to go edit them. My 8 o'clock class was like all weird. I had to fix it after the fact. And then I went in and checked our Zoom meeting stuff before our class started, and it said it was set up for like general mountain time. I mean, it was like really weird. So I fixed it. It should be fine going forward. Just kind of keeping in mind it was a little bit weird this morning, our Zoom links for them. Anyway, just a couple of quick notes before we start. We have, we have a quiz tomorrow. Quiz tomorrow is on just chapter 2.9, okay? So make sure that you've got a pretty good grasp on the homework, because the homework is going to be the basis for what the quiz is going to look like. But the homework is also due 2.9. It's only 2.9. That's due, excuse me, it's due tomorrow midnight. And our quiz will also again be a 24-hour window availability. So keep that in mind when you're working on the quiz. I can spend some time this morning talking about, we're going to do Appendix A, but I have some time I can talk about homework for chapter 2.9. I can answer some homework questions. We also have time tomorrow before in class, because we're only doing these 2 chapter sections this week. So tomorrow in class, I can answer some homework questions for 2.9. We can go over and discuss those. So you can help get you prepared for the quiz and the homeworks themselves. So with that said, does anybody have homework, a particularly pressing homework question on 2.9? Keep in mind, you can do it tonight and then ask me tomorrow, and then we can go over them in class tomorrow. I suspect tomorrow we're going to be number 24. Yeah, great. So I suspect we're going to be, you know, leaving early tomorrow in class, because we don't have, oh, excuse me, don't have a new chapter to discuss tomorrow. So let's do this. This is this homework, chapter 2.9, and we're going to do question 24. Okay, good. All right, so question 24 says we're going to prove the composition formula. Okay. All right, so we've got this formula: sine of the inverse tangent of x is equal to x all over 1 plus x squared radical. Okay, so we're going to be working through this one here, so bear with me as we work it through. All right, so first off, what I'm going to say is I'm going to make some assumptions. So I'm going to say the tangent of theta is equal to x. Okay, I'm going to restrict theta to be an element of the range of values minus pi over 2 to positive pi over 2. You remember the other day when we were working through our inverse trig functions, and when we look at our tangent function, the tangent has asymptotes at repetitions of pi over 2, right? And so I've got, you know, the tangent function, I've got these vertical asymptote minus pi over 2, positive pi over 2, and then that design repeats itself over and over again infinitely, right? But when we want to take the inverse of our tangent function, in order to make sure that our inverse tangent function is a function, we restrict our domain on our tangent function so that our inverse tangent function will be a function, right? So this is what we're doing here. We're saying tangent of theta equals x, but I'm going to restrict my values of theta. I'm not going to include, because I've got asymptotes, but I'm going to restrict it. So when I think about my inverse tangent, it's going to be a function as well. So if I take the reciprocal, my cotangent of theta is equal to 1 over x. All I did was just flip that equation, okay? Now I can exploit, remember our Pythagorean identity. This is our Pythagorean identity, right? 1 plus cotangent squared equals cosecant squared, okay, Pythagorean. So now I'm going to start thinking about putting things through. So the sine of our inverse tangent of x equals the sine of theta. Okay, because think about like what happens, what my inverse tangent is equal to, and then how that actually works when I do this composition here, which is equal to 1 over, excuse me, 1 over the cosecant of theta, 1 over that, okay? Which means I can say this is equal to 1 over plus or minus radical cotangent squared of theta plus 1. And that comes from my Pythagorean identity. Okay, so I'm plugging in. It's plus or minus because we took the square root of it. Okay, so now based on this, I'm going to make some assumptions about stuff. So my sine of theta is positive, it's greater than 0, if and only if, this IFF is not a spelling mistake, it means if and only if theta is an element of 0 to pi over 2. Okay, so from 0 to pi over 2, our sine of theta, this is our positive aspect of the sine of theta. Okay, and that's true if and only if x is positive. Okay, so we go back up to here. Okay, so therefore, what that means is on this, how does that relate to our square root? So therefore, I'm going to take the positive square root in the denominator when x is positive. And I'm going to take the negative square root when x is negative, right? When x is less than 0. Okay. Now what I'm going to do is I'm going to multiply top and bottom by x equals the tangent of theta. Okay, so let's do that. So I'm going to get 1 over plus or minus tangent squared plus 1 radical, and that's going to equal to 1 over plus or minus. This is going to be 1 over x squared plus 1. Okay, so we did this. We're basically substituting in x equals tangent of theta. We're plugging that in here. We're going to get 1 over. Remember how we said cotangent was 1 over x, right? So cotangent is 1 over x. Then if I plug in 1 over x, but it's squared, it's cotangent squared. So this is 1 over x squared plus 1. Okay, which is going to equal to, once I square it out, combine all like terms, and then, you know, take care of things, I'm going to get x all over squared plus 1 square root. Okay, let's do that. You guys have another question on 2.9 you want me to get ready for while you're writing this down? I'll put it into the chat if you want. You guys can think about it too, and then ask me tomorrow in class. We can spend some time talking about homework for 2.9 tomorrow in class, because I won't be introducing a new chapter section tomorrow. If you want to think about it, we can talk about 2.9 and Appendix A, even though Appendix A is due next week. Okay. Any more questions on 2.9? You guys all have this here? All right, I'll post the video for it later too, so you guys can see. Okay, so today we're going to be talking about chapter Appendix A, which is about how do we parameterize curves, what are parameterized curves, and how do we use them to describe motion. And then we're going to build on some of the stuff that we've been talking about with derivatives and whatnot. We're going to describe that with parameterization curves. Okay, so let's just talk about a definition first. Okay, so I'm going to, of our parameterized curve. Okay, so first off, I'm going to draw a picture. I like drawing pictures, and then we'll come up with words. So at time t equals 0. So say I've got this parameter, which usually represents time in seconds or whatever. We usually talk about it in terms of seconds. So at time t equals 0, I have an x position and a y position. Okay, my x is given as a function of t and my y is given as a function of t. So I'm here. Then, you know, our path travels along this path here, right? And say then at time t equals 4, our position is here. I've gone x and I've gone y, okay? And then our path kind of moves this way. Do this as our motion, our direction of motion here. And this point here is given by function of time and a function of time. So our x coordinate is given as a function of time. And our y is given as a function of time. Okay. And then we're just going to keep on going, right? So I'm going to draw this here. So this here, this is our curve. We call it C of t. And C of t is both f of t and g of t. So this represents our x and this represents our y. So parameterized curve talks about t, time, and then x as a function of t and y as a function of t. So it's no longer like y as a function of x. It's basically x of t and y of t, independent functions, okay? So let's talk about it in terms of motion, right? So I've got this, a particle moving along curve C, sorry, with position equal to our x position and our y position. And this is all as a function of time, which is represented by the parameter t, okay? So I would say, to describe my x and my y, I'd say my x was equal to, like we did before, f of t, and my y is equal to g of t. So I've basically taken out, instead of saying y is a function of x, I'm now saying y is a function of time and then x is a function of time, okay? And this is going to give me parametric equations. And typically, and in this class, we can assume that t is a real number, okay? And then I could say position p of t is equal to f of t, g of t, or I can then write p of t is equal to my x function and my y function, and my x coordinate and my y coordinate. Okay, so let's do like an example so you can just kind of see what this looks like. So example 1 on our lecture examples page, right? So we've got want to sketch a curve with the parametric equations for x and for y. So we're going to talk about how we do that. I don't know if you guys did this in middle school or high school when you're first learning algebra, right? Where you learn you have an XY table. So you have like, you choose inputs on your X and you plug them into the equation, you come up with Y values. But that X and that Y give you a coordinate, an ordered pair coordinate that you can then plot. And you plot all those coordinates, all those ordered pairs, and you connect the dots. And now you have a curve. This is your Y as a function of X. We're going to do something similar here, except that we're going to set up a T, X, and Y table. And we're going to use that to help us plot out what this parametric graph looks like. So I've got my T. I'm going to choose values for T. And I've got my X, which is given by 2T minus 4. And I've got my Y, which is given by 3 plus T squared. And then I've got my graph. This is my X, and this is my Y. And I'm gonna let's put up. Okay, so I've got my X and my Y plotted out here. So let's do this. I'm going to choose values. I like to choose values around 0, right? So I choose minus 2. I'm going to plug that in. So everywhere I see a T, so 2 times a minus 2 minus 4 gives you minus 8. Plug it in here. Minus 2 squared plus 3 is going to give me a 7. So now I have this point, minus 8, 7. And then I'll put it in red. This is where T equals minus 2. Okay. I'm going to choose 0 for T. So I plug in, right? Everywhere I see a T, I plug in 0. So I get minus 4. Everywhere I plug in T, everywhere I see a T, I plug in 0, and I'm going to get 3. So minus 4, 3 gives me another point, and this is t equals 0. Okay, let's do a couple more. So t equals 2, I'm going to plug it in here. I'm going to get 0. So when t equals 2, oops, I'll do this here. So when t equals 2, I'm going to get 7. So 0, 7 is another point. T equals 2. And then I'm going to plug in 4 here, and I'm going to get 4 and 19. So I'm going to get 4 and 19, and I'm going to write down t equals 4. And I'm going to connect the dots. And this is the motion. This is our direction. So this is, we're heading this way, right? Okay, that's our curve, right? So t equals -2, then t equals 0, then t equals 4. So this is like the direction that we're actually heading in, okay? And I can keep on going for these values of t and then come up with, you know, curves and what does it look like, okay? So this is not y as a function of x. This is x as a function of t and y as a function of t, which is why I put the t's on the graph. So you can see, like, you know, this represents a curve, a path that we're following, okay? Okay. Right, so y equals f of x. I can parameterize that. I can parameterize it like this. So c of t equals t f of t. So then I could say just as an example, if y is equal to x squared, then my x is going to equal to t, and then y will equal to t squared. So then my c of t is going to look like t comma t squared. Okay, so I'm choosing a value for x. X tends to be t, right? And then, because it's like my input, and then I've got it like this. So I can say y equals e to the x, right? So if x again is equal to t, then y equals e to the t. So this c of t is going to look like t comma e to the t. It's a little bit of trial and error, right? In terms of like how you're trying to parameterize it and what the graph is going to look like. But what it does is parameterized curves allow us to describe curves, so parameterized functions too, functions allow us to describe curves that are not graphs of functions. Right, a graph of a function is y equals f of x, right? This is my input, this is my output, right? But now I'm looking at x independently as a function of t, and then y is a function of t. So it describes my x position, it describes my y position, say, for example. Okay. I'm looking at example 2 on our lecture examples, and it says, describe the parametric curve in the form of y equals f of x. And we're given it in terms of the parameters c of t equals 2t minus 4 and y is 3 plus t squared. But I want to get it back into the form of y equals f of x. I want to see what it looks like. So I want to basically solve for y as a function of x. That's my goal. Y equals f of x. Okay. So the first thing I have to do is I have to express t in terms of x. Okay, that means I'm going to go into my parameterized function, and I'm going to say my x component is equal to 2t minus 4, right? Because let's break this down. X is equal to 2t minus 4. Y is equal to 3 plus t squared, right? I'm just taking out my x component, my y component. I'm writing them separately. So x equals 2t minus 4, but I want this t equals something, right? So I'm going to add 4 to both sides. I'm going to divide by 2. It's x plus 4, then divided by 2. So then I'm going to get t equals 1/2 x plus 2, right? So here, right, you can see how I got 1/2 x plus 2. So now that's just in terms of x. I have to take this t, and then I'm going to substitute this t into the y of t equation, and that's going to give me y of x. Y is a function of x, right? So if I've got y equals 3 plus t squared, right, I'm going to take this t and I'm going to plug it into here. Okay, and I'm going to have y as a function of x. So it's going to look like y equals 3 plus 1/2 x plus 2 squared, quantity squared. I could leave it like that. I'm going to FOIL it out and then combine all the like terms. So I'm going to rewrite it. This is also what I call make it look pretty, right? So this is going to look like y equals 7 plus 2x plus 1/4 x squared. I'm going to rewrite it so that it's like descending. So y equals 1/4 x squared plus 2x plus 7. Now y is a function of x, okay, instead of what we started with, which was y and x are both functions of t. Now I basically rewrote it, so now it's just a function of y is a function of x. Okay. Let you guys finish writing that, and then we'll talk about example 3. Okay. Right. So example 3 says, we've got a bullet firing out of a gun. So bullet's following this trajectory, position x as a function of time, 80 times t. It's going this way. My y position is given as 200t minus 4.9 t squared. So the y position, right, it's going to be decreasing in its y-ness, right, in its height. We're going to do this until it hits the ground. T is in seconds, the distance is in meters. Okay, so this is our position. So we want to find the bullet's height at t equals 5 seconds and then find the maximum height. Height implies that we're dealing with the y of t. Okay, that's the y of t part. The x position is where we are along the horizontal axis. The y position is our height. Okay, so now we want to find the bullet's height at t equals 5. So I'm going to go y of 5 equals 200 times 5 minus 4.9, 5 squared. Right? So I plug this in and I'm going to get this was equal to 877.5 meters. Okay, what is the height? Where is it after 5 seconds after being fired? This is where it's at. What's its height? Okay. I don't have to worry about the x position because it just said what's the height. B says find the maximum height. Maximum height implies a critical point for y of t. Okay, let's take a look at our y of t function for a minute. So y of t equals 200t minus 4.9 t squared. It's a parabola with a negative leading term. A negative leading term on my parabola means, right, it's a downward facing parabola, which means I only have a maximum. Okay, so our maximum height, right, it's a critical point. We know because it's a parabola, it's only going to have one. Now, technically, I should probably take like the first derivative test or second derivative test, but I know my parabolas, right? So maximum height, critical point, which means I have to take the derivative. Okay, so 200 minus 4.9 times 2 times t, which is equal to 200 minus 9.8 t. Right, to find our critical point, we have to set it equal to 0 and then solve for t. That's going to give us the time at which we reach our maximum. Okay, so give us the time. So when I do this, I'm going to get t equals 200 divided by 9.8, which I got, my calculator was roughly 20.4 seconds. So at 20.4 seconds, we've reached our maximum height. So that's how we think about it. At 20.4 seconds, reached our maximum height. But they asked us, what is the height? They didn't say when does it occur. They said, what is the height? So that means I have to take this time and I have to plug it into my y function to find out what's the height associated with that maximum time. So I'm going to go y this is not my derivative. I plug it into my function y of 20.4 equals 200 times 20.4 minus 4.9, 20.4 squared. Plug it in, multiply it out, combine it. I'm going to get, this was approximately equal to 2,041 meters. And like I said, I know it's a maximum because it's a downward facing parabola. It only has one maximum here. That's kind of what it means when we're interpreting what it's being asked, right? So when they're asking height, we're just talking about the y, okay? You guys good? Okay, so let's take a look. We're going to do parameterizations of various shapes. It's kind of a neat thing. It's a little bit of geometry. So the first thing we're going to start off with is parameterizing a line. The theorem of a line. This is a straight line, like y equals mx plus b, or a point slope kind of a line. Okay, so we're going to talk about parameterization of that. Okay, so two different things we want to think about. I can give you a point and a slope, and then we'll talk about how we parameterize that. So we'll do that part first. So the line, and spell OU through point P, which has x coordinate and y coordinate AB, and it has a slope M. I don't know what it is, M. I'm just going to use the variable. I can say this is parameterized by our equation. So I need to do the x and the y components. So my x position is given by the x part of my point plus, right, my, I'm going to break this up. I'm going to tell you what these things are in just a minute. R times t. And then my y is given by the b point plus s times t. And I'll tell you what these are in just a second. Where m is equal to s over r, right? So think about it like this. Our slope is the change in y over the change in x, remember? Change in y over the change in x, our rise over the run, okay? So s is just a variable that represents our y change, our y component of our slope. That's what gets multiplied here. R represents our x component of our slope. That's what gets multiplied here, okay? And then t is our parameter. It's a real number, so it's, you know, minus infinity to positive infinity. And then we want to also specify that r can't be equal to 0, but this we can have any value of s and r, besides r not being able to equal to 0. Okay, so we're given a point, we're given a slope, we're going to break this up. Our parameterized curve, x as a function of t, y as a function of t. Let's say I'm going to go from point P to point Q. Okay, so the line through the points P, which is A to B, A and B, and Q, which is C, D. Okay, so you can think about it as being, I'm going to start at P and I'm going to end at Q. That's how we can think about it, right? It's a little arbitrary where we start, where we end. Okay, so if I start at P, I consider that my initial point, and I end at Q, I'm going to consider that my terminal point, which means that I need to think about what we call a displacement vector. I'm getting into a little bit more detail than we need, but I just want to throw it out there. So our displacement vector is basically the subtraction, the difference between our terminal point minus our initial point. Okay, so now if I've said my terminal point is Q, which is CD, and my initial point is P, which is AB, okay, my equation for a parameterized line through these points goes like this, right? I've got my line as a function of t, and I do my initial point, plus I've got my parameter t times my displacement vector. We're going to break this up in terms of our x component and our y component again. So I'm going to say my x is equal to my initial point. We said that p was our initial point, so p is ab. So I'm going to take the x component out of my initial point, plus t is my parameter. Now to get my displacement, remember I said terminal minus initial. I'm just going to do the y components of my terminal and the y component of my initial. So that's going to be, I'm sorry, this is x, c minus a. Sorry, my bad. I meant x because we're doing x right now. So c minus a, this is going to be my x component and my x component, but terminal minus initial. And the y is going to be, right, the y component of my initial point, which is b. T, that's my parameter. And now I'm going to do the y components, d minus b. If I had said P was my initial, Q was my initial point and P was my terminal point, these would just be flipped, right? This would be A minus C, this would be B minus D, and then this would be C and D instead of A and B. It's arbitrary how you want to choose it, but we've basically said we're starting at P and ending at Q. This makes it, if it's going to be a line segment. If it's a line and it goes in this direction, then I don't put restrictions on T, but if it's a line segment, then T is between 0 and 1. Choosing 0 for T is going to give me my P value. Okay, choosing 1 for T is going to give me my Q value. Okay, so this basically says I'm going to start at P and I'm going to end at Q. Okay, this is how we parameterize a straight line. Y equals mx plus b, or our point slope form. So example 4 says, find the parametric equation for the line through the point 3 minus 1 with slope m equals 4. So this is, we're just going to go working our way through basically part A on here. Okay, so let's write down what we have. So we said this is our point, this is our x and our y, which would have been our AB in the past. So our m is equal to, we said s over r, which is 4, which is also, I can write it as 4 over 1, right? So my s is equal to 4 and my r is equal to 1, okay? So when I think about putting that into an equation, my x and my y, so my x is going to be my x component of my point plus t times my x component, which is my 1. I'm not going to write it. Y is going to be minus 1. That's my y component of my point plus s 4 times t. Okay, I can leave it like this, or I can put them together into a single equation. These are equivalent. Okay. We often like to write it this way because it's just a single equation, and then I can save space. They're more concise. Okay. That's a line. Let's talk about other shapes. So we're going to talk about parameterization of a circle. Okay, so let's go back. Remember we did our unit circle before, right? We drew up like cosine and sine with our unit circle. So first I'm going to draw out an axis. This. Here's my x and my y. And I'm going to put my my circle. I'm going to center it initially at the origin just so we can visualize it, and then I'll move it over and up. We'll move it over and up in just a minute, but let's do it first here. So I've got a circle of radius r. So it's not a unit circle anymore. It's got a radius, right, r, and it's still making an angle with the x-axis, right? And then this is our center. I'll say AB is the center, and then r is our radius. Okay, so here if we're centered at the origin, right, and I think about how far out have I gone in the x direction. So remember how we did this before. We said, well, if I'm going to take, cosine of theta is going to equal to adjacent over hypotenuse, which means x is going to equal to my radius times the cosine of theta. Okay, do this again with our y. So I'm going to say my sine of theta, that's opposite over hypotenuse. This is going to be y over our radius. So this is y equals r sine of theta. You know, what happens is this forms the basis of our parametric representation, where theta is equal to our parameter. Okay, so no longer is it what's my xy coordinate, it's cosine of theta, oops, times our radius, and then our sine of theta. Okay, that's a point on our circle, our cosine of theta, comma, our sine of theta. Okay, so now here, it's the same deal. We've got sort of our imaginary axis here with our x and our y, and this is our radius. The only difference is that instead of being at the origin, I'm at a center point. Maybe I've gone over 3 and I've gone up 4, so my center is up here at 3, 4, say for example. So to write this in terms of parameters, how I need to represent it is I have to take into account how far over in the x I've gone. That's my a. Right, plus my parameterization, r cosine of theta. My y, how far up I've gone, my translation, how far up I've gone, that's my b, plus r sine of theta. That gives me the point along my circumference. So this is our parameterization with theta as our parameter. I can also write this as, we'll call it c of theta, which is going to be a plus r cosine of theta, b plus r sine of theta. And that's the parameterization of our circle. Individually speaking like that. Okay. And that's important. We can use that now to help us describe other things. Okay. Let you guys finish writing that, and then we're going to talk about example 5, which is an ellipse. Ellipses are similar to circles, except they can be stretched out in one direction or stretched out in the other. Okay, so they don't have a constant radius. They've got an x and a y that we need to think about. All right, we're going to talk about example 5, which says we're going to parameterize an ellipse, and we want to plot it with a equals 4 and b equals 2. So let's remember this is x over a squared plus y over b squared equals 1. That's our sort of generic equation for an ellipse, right? So let's remember our curve c of t equals a cosine of t, b sine of t. And I didn't tell you this was centered at the origin. You needed to know that too. Centered at the origin. Okay, so now we're going to be dealing, t is our angle, right? That's our parameter. And I'm going to restrict t to be between minus pi and positive pi. And we're gonna plot it too. We'll come up with a plot in a minute. So the first thing that I want to do is I want to show that the equation of the ellipse is satisfied with the parameters that we've chosen. A cosine of t, b sine of t, right? I mean, like I said, an ellipse is similar, you know, to a circle, except that instead of it being a radius, a consistent radius, we've got how much in the x direction and how much in the y direction. Okay, so if I plug in, this is x equals a cosine of t, y equals b sine of t. I'm going to plug those into my x over a quantity squared, y over b quantity squared equations and see, does the equality hold true? A cosine of t divided by a squared. This comes from our ellipse equation. Plus b sine of t all over b quantity squared equals 1. Now my a's are going to cancel. My b's are going to cancel. Okay, and what I'm left with is cosine squared of t plus sine squared of t equals 1. And that's true because of the Pythagorean identity. So our ellipse equation is satisfied by the parameters that we've chosen. Okay, so that's good. All right, so now let's go ahead and plot it. Okay, so I need to set up a t, x, and y table. So I'm going to say t, I'm going to choose values of t You can choose values of x equals, I said a was equal to 4, so 4 cosine of t. And then y, we said y, b was equal to 2, so b sine of t, 2 sine of t. And then I'm going to set up my graph to look like this. Here's my x, here's my y. Now I know 4 tells me how far out I'm going to go in the x directions, minus plus or minus 4. The 2 tells me how far up I'm going to go, how far down I'm going to go in my y directions. All right, kind of gives me a bounding point. So let's choose values of t. Now remember t, we restricted between minus pi and pi. Okay, so I'm going to choose, I know that there's a symmetry here. Remember our ellipse has a symmetry. So I'm going to start off, only do part. So t equals 0, plug in cosine of 0 times 4 gives me 4. 0. So this means x is equal to 4, y is equal to 0. I can plot a point. When t equals, I'm going to choose, this is in radians, so pi over 6. I'm going to get 2 radical 3. This is 1. Get a value right over there. I'm going to choose pi over 3. And I'm going to get 2 radical 3. And I'm going to choose pi over 2. And I'm going to get 0 and 2. Okay, I'm just going to keep going. I can actually stop right here because there's a symmetry here as well. But I'll keep going. We'll do the half of our ellipse. So 2 pi over 3. I'm going to get minus 2 and radical 3. Here. 5 pi over 6. I'm going to get minus 2 radical 3 and 1. And get pi minus 4 and 0 here. And I'm going to use my symmetry. I don't have to go through and do minus pi to 0, okay, to do the other half of the equation, right? Like I said, I could have even just stopped with just quadrant 1 and then reflected it this way. But I'm going to use symmetry. But the other half of the ellipse, this is going to be minus pi is less than t, which is less than 0. So that's going from, right, the whole minus pi to 0 part of the t. X-axis, right? So I'm just going to do these here. I know that there's a symmetry. Okay, so that gives me a curve that looks like this, right? Okay. Now, normally what you could do is you could write a computer program, right, that takes in, that loops through values of t, right, from minus pi to positive pi. It gives you like, thousands of points. You're going to take those thousands of points and you're going to plot them onto your graph. Okay. Well, you guys finish writing that, and then we'll talk about other types of curves. You guys all set with that? All right. So one thing to note that I want to point out is that parametric curve is a path, okay, but it's not unique. It's not a unique function. So parameterizations are not unique, right? So for example, right, I've got my parabola, y equals x squared. That's unique, right? I've got this parabolic equation, right? But if I parameterize it so that x is equal to t, then y is equal to t squared. Okay, that's going to give me a graph. I can also represent it as t cubed to t6. That's going to give me the same type of representation. Or I can say t to the 5th, t to the 10th. These are all paths, okay, that satisfy still the y equals x squared, okay, function, but they're not unique. Okay, so just an example, just to kind of keep it in mind. Okay, instead of like y equals f of x, that's a unique function. Parameterizations of a curve are not. Okay, so another geometry. We're going to talk about a cycloid. Cycloid's really interesting. This is kind of like a neat experiment. I don't know if you guys did this in high school when you're first learning trig functions, but you can take a can, like a circular can or a cup or something like that. You want it to be perfectly circular, and like you poke a little hole in the center so you can keep your center point oriented, keep it straight, and then you can like tape a pencil or a pen or marker or something to the circumference, to the outside edge, or really on a can you'd want to do it on the inside edge, and then you roll the can, and then it'll trace this curve, right? So it's a curve traced by a point on the circumference of a rolling wheel. And I'll try to draw it out here just so you can visualize. This is our, say, our ground, for example, and this is our height. So I'm going to do this, and then I'm going to put a little red asterisk here so you can follow. That's like where we put our pencil, right? And this you can think of, I'm putting it here at this, we're going to draw like a bigger picture later. So I'm going to roll the can this way, right? I'm rolling it as we go. I'm rolling the can. So now what happens is, as we roll the can, right, our center stays in the same spot, but that little pencil that we have attached to the outside edge moves along, right? So it starts here, and then it's going to go, let's see if I can get this right, right there. And draw this again. Bear with me here, I'm not a great artist. It's a neat experiment if you get a chance to do it. I always like to see. Bear with me here. Oh, there we go. And it hits. And then basically what happens is we keep rolling this, and it goes like this, and it keeps rolling. So it's going to take, right, in terms of distance, that'll be 2 pi, right? It reaches its height at pi. And then you can imagine this would be 4 pi. Some multiples of 2 pi are where it's going to be hitting our axis again, like this, right? So it completes a whole cycle in 2 pi. Okay. So if I want to parameterize, we're spending time on the cycloid. It seems a little esoteric, but it actually is used quite a bit in like engineering types of problems. That's why we're taking a look at it. So let's talk about how we parameterize this. Okay, so we want to parameterize our cycloid. So I've got point P is at the origin at time t equals 0. Okay, so it's at the origin. Our x of t is given as t minus the sine of t. Now remember, look what I did. My radius, I'm going to draw this out in a different color. My radius is equal to 1, right? We're going to talk about generic, like if a radius is not equal to 1, what does the graph look like? We're going to start off just with the radius equal to 1. Radius equals 1 unit. Okay, so this is t minus sine of t. My y position is given as 1 minus the cosine of t. I'll tell you where these values come from in just a minute. Okay, so how I got these equations comes, I'm going to zoom in. So I'm going to take this thing here and I'm going to turn it just a little bit, right? And I'm going to zoom in. So imagine here's our center point. Okay, this is our radius. It's a 1 unit radius. On this particular example, this is P, our point P. Okay, the angle T is the angle that we're making, right? So this is where we put our marker. This is what's tracing the thing. Okay, this has x coordinate. This has y coordinate. This is 1, and this right here is 0, 0. Okay, so this is position P, right, at time T. Okay, as we roll along. Okay, so you can imagine, right, this is what's tracing our position, right? This point right here. This is where we put our little asterisk, our pencil. Okay, so I'm going to take this triangle here and I'm going to zoom in. Okay, a little bit more, like you can imagine I've got this triangle like that. Okay, so let's zoom in on this triangle. So, like this. I'm sorry, you can't see what I'm doing. There. This is t, x, y, 1. So this whole thing is equal to 1. This is t right there. Okay. And then because t is here, this bit forms cosine of t. This is our radius is equal to 1. Our radius is equal to 1 because this whole thing is equal to 1. And then this is our sine of t, okay, because it's opposite over hypotenuse. This is cosine of t, or x is adjacent over hypotenuse. Okay, so that's where we're getting these things. So then our position has coordinates x equals t, right, minus the sine of t, right? Because I've gone t distance minus the sine of t, okay? From here to here, minus the sine of t. My y is 1 minus cosine of t, right? Because I've gone, this whole length is 1, and I'm going to subtract cosine of t. That's going to give me this spot right there, because that's where these things are coming from. Okay, now, if I make this a radius equal to r, right? This is radius equal to 1. Let's talk about radius equal to r. So I'm going to have a circle of radius r. My x is going to be r times t minus r sine of t. My y is r minus r cosine of t. This is generic. This is with radius equal to 1. It's kind of easy to think about it with radius equal to 1 and then extend it out to a generic, okay? Because I've got my whole radius minus this bit here gives me my y coordinate. My whole distance t minus this bit here gives you my x coordinate. Okay, p is our xy. That's what we're trying to figure out. P is the thing, right? This is our little asterisk. That's our pencil that's tracing the curve. Okay, so that's your cycloid. Cycloids are neat. Like I said, if you get a chance to do it where you have a can, you fix the center and you attach like a pencil, you can actually roll it and see it make this curve. It's kind of a neat thing. I'll let you guys finish writing that, and then we'll talk about tangent lines. You guys all set? So I've got some parameterized curve, right? It's, you know, doing stuff, and I want to take a look at what's the tangent line? What's the line, right? Our slope line. What's the line that's tangent to a curve at a particular time? I want to talk about tangent lines. So when I talk about tangent lines here, I'm not talking about like sine over cosine. I'm talking about like, you know, our slope of our tangent line. Tangent lines to parameterized curves. Okay, so I've got my curve, C of t, which is equal to, I've got my x of t, and I've got my y of t, right? So whatever, right, x is a function of time, y is a function of time. Put this together, it gives you my x position and my y position. And I'm going to make some assumptions that x of t and y of t are both differentiable. Okay. I also need to assume that the derivative of x is not equal to 0, and it's continuous. Okay, and that's important because to find the line, the tangent line for a parameterized curve, I need to do dy dx is going to be derivative of y with respect to t divided by the derivative of x with respect to t. Okay, so this is y prime of t, x prime of t, right? Remember, our slope is the change in y over the change in x. So when I take the derivative of y, I take the derivative of x. That's why we have to restrict to make sure x is not equal to 0 and that it's continuous. It doesn't have any like holes or anything in there. Just continuities. Okay. So we're breaking down our components, x and y. All right. So let's take a look. Our last example is asking just that. So we've got this, example 6. T squared plus 1, comma, t cubed minus 4t. We want to find the equation for the tangent line at t equals 3. So the first thing I'm going to do is I'm going to break this down into my components. My x of t is t squared plus 1. My y of t is t cubed minus 4 times t. My tangent line is my derivative of x, my derivative of y over derivative of x. Okay, so dy dx equals y prime of t all over x prime of t. So I'm going to take my derivative of y, 3t squared minus 4 all over derivative of x, 2t. Okay, this is at t equals 3. So now I get to plug in, right? Everywhere I see a t, I plug in a 3. So this is 3 times 3 squared minus 4, 2 times 3. So I'm going to get 23 all over 6 is the slope of the tangent line at t equals 3 of my parameterized curve. Okay. All right. Part B says, oh, I need the equation. Sorry, I didn't do the rest of it. My bad. Find the equation for the tangent line. So I have to plug this in at t equals 3. I'm going to plug in to my equation to find out what's my xy coordinate. So it's the point. So that's going to be 3 squared plus 1, comma, 3 cubed minus 4 times 3. It's going to give me a coordinate, right? When I plug this in, I'm going to get that's equal to 10, comma 15. So I put this together. This is our point on tangent line at t equals 3. So I'll put this together into point slope form. So I'm going to say y minus 15 equals 23 over 6, x minus 10. And that gives me the equation of my tangent line. Okay. Part B says, find the points where our tangent line is horizontal. Tangent line is horizontal when our derivative is equal to 0. But now, because we have two functions, y of d over x of d, I have to be very careful. This is true when y prime of t is equal to 0, but not x prime of t equal to 0, right? I have to be very careful. I'm only checking here. I find those values of t, and I have to check to make sure that it doesn't make my x prime equal to 0. If x prime is equal to 0, I'm going to get a divide by 0 problem. So I have to only check for my y prime. So y of t, we said before we did this, right? 3t squared minus 4. Set that equal to 0 and solve for t. Okay, so when I solve for t, I'm going to get t is equal to plus or minus 2 divided by radical 3. Divided by radical 3. So at these values here, right, I need to do a quick check to make sure my x prime of plus or minus 2 divided by radical 3 is not equal to 0. Because if it causes my x prime to be equal to 0, I have to discard that t value. Okay, so it's possible, if it's true that I have the same values for x prime and y prime, then I could say there's nothing. There's no point where the tangent line is going to be equal to 0. All right. All right. So I checked it. I checked it offline. 2 divided by radical 3. This was not equal to 0, so that one's okay. I checked it offline. Negative 2 divided by radical 3. This one wasn't equal to 0, so that one was okay. So they're both okay. Both points. Okay. Both t values are okay. So now with that check done, I'm going to look for, it said where, at what point is my tangent line horizontal. So that means I'm going to take this t, I'm going to plug it into my c of t and get coordinate. Where tangent line is horizontal. Okay, so we plugged it into our c. So c of positive 2 divided by radical 3 is going to give me 7/3, 16 divided by 3 radical 3. I plugged it in, I did it offline already. I'm going to do c of minus 2 divided by radical 3, and I'm going to get 7/3 minus 16 over 3 radical. These are the coordinates where our parameterized curve has a slope equal to 0. Okay, and that's it. And that's Appendix A, Parameterized Curves. Tomorrow I can answer questions on the homework for 2.9 and Appendix A if you want. And then we can even break early because we'll have a quiz tomorrow. Okay, guys? Have a great day.
Thank you. Have a good day.
Bye.
Thank
Take
you.
care.
Thank
Take care.
you.
Thank you.
Bye. Take care.